For most of the last 100 years, the animal in your head, when you picture Tyrannosaurus rex, has been more or less the same creature, an upright, scaly monster with a permanent snarl, teeth jutting out over its lower jaw like a row of steak knives that never quite fit inside its own mouth. That image is almost entirely a product of Hollywood, and as it turns out, it's almost entirely wrong. Over roughly the last 3 years, a wave of new research drawing on CT scans, growth ring histology, genetic modeling, and biomechanical simulation has quietly rebuilt T, Rex, from the snout down. The animal that's emerging from that research isn't smaller or less impressive. If anything, it's more dangerous, more strange, and considerably more calculating than the version that's been chasing Jeff Goldblum across movie screens since 1993. This is what the science actually says now. The mouth. Nobody expected. Start with the single most recognizable feature of the whole animal, the teeth. For decades, the default assumption, reinforced by paleo art and every dinosaur movie made since the 1980s, was that T, Rex's teeth, sat permanently exposed, more or less like a crocodile's, jutting visibly over the jawline even with the mouth fully closed. In 2023, a team led by paleontologist Thomas Cullen at Auburn University put that assumption to a direct test, and the results, published in the journal Science, upended it. Cullen and his collaborators compared skull length against tooth size across more than 20 theropod dinosaurs and a range of living reptiles, including monitor lizards and Komodo dragons, animals with lips that fully cover teeth every bit as large, proportionally, as anything found in a tyrannosaur's jaw. What they found was that theropod teeth, T-Rex included, were never actually too large for the skull to accommodate them behind a closed, lipped mouth. The old crocodile comparison, it turned out, was the wrong reference animal entirely. The team backed that conclusion up with 2 additional lines of evidence. First, they examined wear patterns on fossilized tooth enamel. Crocodile teeth, permanently exposed to open air, wear down unevenly and relatively quickly. The same way a blade left out in the weather, dulls faster than one kept sheathed. T-Rex teeth showed nothing like that pattern. The enamel was far more evenly preserved, consistent with teeth that spent most of their time bathed in saliva behind soft tissue, rather than sitting exposed to the air around the clock. Second, they looked at the tiny nutrient foramina, small holes in the jawbone that carry blood vessels and nerve endings to the surrounding soft tissue. In crocodiles, these holes are scattered fairly randomly across the snout. In lipped reptiles, like monitor lizards, they run in a single organized line along the jaw margin, tracking exactly where a lip's soft tissue would need blood supply. T-Rex's jaw matched the lizard pattern, not the crocodile one. Put together, 3 independent lines of evidence, skull-to-tooth ratio, enamel wear, and bone vascular pattern, all pointed the same direction. T-Rex's teeth almost certainly sat behind scaly, lizard-like lips, closer in overall look to an enormous monitor lizard than to anything resembling a crocodile's grin. Cullen has been careful to note that this remains an inference rather than a certainty, since no theropod fossil has yet preserved actual soft facial tissue in enough detail to settle the question outright. But the anatomical case, built from 3 separate directions, is currently about as strong as indirect fossil evidence gets. The detail matters for more than just appearance. Keeping enamel continuously moist behind soft tissue helps prevent the kind of microscopic brittleness that leads to chipping and cracking under stress, which is a serious consideration for an animal whose entire hunting strategy depended on a small number of enormous, slow-growing teeth. Sectioned tyrannosaur teeth, studied under a microscope, show growth increments suggesting individual teeth could take well over a year to fully form and replace. An animal that couldn't afford to damage its primary weapon casually had every reason, evolutionarily speaking, to keep those teeth protected. Rewriting the family tree mid-growth. If the lips reshaped what T-Rex looked like, a separate line of research over the past 2 years has reshaped who actually belonged in the species at all, and the story starts with 2 of the most famous juvenile T. Rex fossils ever found, specimens nicknamed Jane and Petey. For decades, Jane and Petey served as the primary reference points for what a teenage T-Rex looked like, how it grew, and how it might have hunted differently from a full-grown adult. That assumption came under serious pressure starting in 2025. Paleontologists Lindsay Zano of the North Carolina Museum of Natural Sciences and James Napoli of Stony Brook University published an exhaustive reanalysis in the journal Nature, built around a remarkably complete tyrannosaur skeleton nicknamed Bloody Mary, part of the famous dueling dinosaurs fossil pair recovered from Montana's Hell Creek Formation, where a tyrannosaur and a triceratops were found locked together in what appears to be the aftermath of an ancient confrontation. Zano and Napoli's analysis found that this specimen, despite weighing a fraction of what a full-grown T-Rex weighs, showed clear signs of skeletal maturity. Growth rings inside its bones had compressed and stacked together in the pattern that indicates an animal has stopped growing, not one still climbing toward adult size. Beyond that, the skeleton showed anatomical features that don't shift as an animal matures, the kind of fixed traits paleontologists use to distinguish species rather than developmental stages, and those features didn't match T. rex. The animal had proportionally longer, more robust forelimbs, larger hand and finger bones, a different pattern of skull sinuses and nerve pathways, and fewer vertebrae in its tail than any known T. Rex specimen at any age. The conclusion? This wasn't a juvenile T. rex at all. It was an adult of an entirely separate, smaller tyrannosaur species, one that had actually been named decades earlier in 1988, based on a partial skull nicknamed the Cleveland skull. That original name, proposed by paleontologist Robert Backer and largely dismissed by the wider scientific community for years, was Nanotyrannus lancensis, the pygmy tyrant. Zano and Napoli's 2025 paper didn't just resurrect that name, it went further, identifying Jane specifically as a second distinct Nanotyrannus species, which they named Nanotyrannus letheus, after the river Lethe from Greek mythology, a nod to how long the animal had effectively been forgotten in plain sight inside museum collections labeled as juvenile T. rex. A separate, independently conducted study reached a strikingly similar conclusion around the same time using an entirely different piece of anatomy. Researchers examined a small tube-shaped throat bone called the hyoid, recovered from the original 1980s Cleveland skull specimen. Like limb bones, hyoids are capable of preserving growth rings, and when researchers sectioned this one, the internal structure matched that of a mature or fully grown animal, rather than a still-developing juvenile, arriving at the same conclusion as Zano and Napoli's team from a completely separate dataset and method. The scientific fallout from this reclassification is significant and still ongoing. For decades, studies of T. rex growth rates, hunting behavior, and juvenile ecology leaned heavily on Jane, Petey, and the Cleveland skull as reference points for what a young T. rex actually looked like and how it lived. If those specimens belong to a different genus entirely, a substantial amount of what paleontologists thought they understood about T. rex's adolescence has to be re-examined from scratch, essentially removing the primary evidence base and starting the investigation over how long it actually took to grow up. With Nanotyrannus specimens pulled out of the growth dataset, a separate 2026 study tackled a more basic question directly. How long did it actually take a real T. rex to reach full size? The long-standing assumption had been rapid growth, reaching an adult weight of roughly 8 tons within about 20 years. Paleontologist Holly Woodward at Oklahoma State University led a team that revisited that assumption using a more rigorous approach, counting growth rings preserved in cross-sections of leg bones from 17 tyrannosaur specimens under polarized light microscopy, a technique that reveals subtle banding invisible to the naked eye. Their conclusion pushed the timeline out considerably further than expected. T. rex likely didn't reach full adult size until somewhere between 35 and 40 years of age, roughly 15 years later than earlier estimates had suggested. That extended growth window carries real behavioral implications. Subadult predators across many living species today tend to be the most active, aggressive, and opportunistic hunters in a population, still building strength and experience without yet carrying the bulk of a full-grown adult. If T. rex spent something on the order of 2 decades in that subadult phase, that's a very long stretch of an animal's life spent in its most behaviorally aggressive hunting window. And once a T. rex did finally reach full size, it arrived there carrying several decades of accumulated hunting experience already built in, a level of behavioral refinement that a faster maturing predator simply wouldn't have had time to develop. Interestingly, Woodward's own team flagged something odd in the data before the Nanotyrannus story had fully settled. 2 of their 17 specimens didn't fit the growth curve cleanly at all. Those 2 outliers were, unsurprisingly in hindsight, Jane and Petey, the same specimens that would shortly be reclassified as an entirely different genus. The growth ring anomaly and the anatomical reclassification, arrived at through completely different methods by different research teams, ended up reinforcing each other. A bigger animal. Then the record books show, size estimates for T. rex have shifted more than once over the past decade, and the most recent numbers point in a genuinely startling direction. The largest confirmed T. rex specimen recovered so far is a skeleton nicknamed Scotty, discovered in Saskatchewan and painstakingly excavated over more than a decade. Based on the circumference of its femur, a standard method for estimating body mass in large extinct animals, researchers estimate Scotty weighed somewhere in the neighborhood of 8,800 kilograms, close to 9 metric tons, at a length of roughly 13 meters, making it the largest terrestrial predator confirmed from the fossil record. For years, Scotty was treated as something close to the practical upper limit of how large a T. rex could realistically grow. A 2024 statistical analysis challenged that assumption directly. Researchers built a probability model incorporating the total estimated T. rex population that ever lived, a figure previous research had placed at roughly 2. 5 billion individuals across the species' entire existence, against the small number of reasonably complete skeletons actually recovered. Fewer than 100. Run that math, and the odds that paleontologists have already happened to unearth the single largest individual that ever lived turn out to be vanishingly small. Based on the statistical spread that population size implies, the analysis suggested the true upper limit for T-Rex body size could be closer to 15 metric tons, roughly 70% heavier than Scotty, with a corresponding length potentially exceeding 15 meters. That's a genuinely large upward revision, and it comes from a statistics rather than a newly discovered giant skeleton, which is worth being clear about. Nobody has actually found a 15-ton T-Rex. What the analysis argues is that, given how few skeletons exist relative to how many animals lived, the true ceiling for the species was almost certainly higher than anything currently sitting in a museum collection, simply because museum collections represent an extremely small, essentially random sample of the total population. Separately, researchers using CT scans of living birds and reptiles, T-Rex's closest surviving relatives, have refined how much soft tissue, muscle, fat, and skin likely covered the skeleton in life. Earlier reconstructions, built using a simpler method of shrink-wrapping skin directly over bone, consistently underestimated how muscular large theropods actually were. The newer, CT-informed reconstructions suggest T-Rex carried noticeably more muscle mass than older artistic depictions implied, particularly around the hips and hind limbs, consistent with an animal built for genuinely powerful, controlled movement rather than simple bulk. Built for speed, not spectacle. Which raises an obvious follow-up question. If T-Rex was more heavily muscled and more powerfully built than previously assumed, how did it actually move? Research published in 2026 combined fossilized trackway evidence with biomechanical simulation to model T. Rex's gait directly, and the resulting picture looks nothing like the ground-shaking, stiff-legged charge popularized on screen. The analysis suggests T-Rex most likely struck the ground toe first, closer to how a large modern bird walks, with shorter, quicker strides relative to its size than earlier models assumed. That gait pattern implies a more stable, controlled walking motion, and crucially, an animal capable of making sharp, precise head movements while on the move, useful for tracking and closing in on prey rather than simply barreling forward. Based on that biomechanical modeling, researchers estimate T-Rex could sustain running speeds somewhere between 18 and 40 kilometers per hour, depending on body mass, with the largest, heaviest individuals running at the slower end of that range. That's still fast enough to outrun a human sprinter, but it also implies an animal that moved with considerably more precision and control than the lumbering, ground-shaking depiction most people have in their heads. The same modeling work extended to juvenile T. Rex, and found something notable. Younger, lighter individuals were significantly faster than their adult counterparts, fast enough to plausibly pursue different prey species than adults would have targeted. That opens up the real possibility that young T-Rex occupied a meaningfully different ecological niche than fully grown adults, chasing faster, smaller prey, rather than competing directly with older individuals for the same food sources. A warm-blooded predator. For most of the 20th century, dinosaurs in general, and T-Rex specifically, were assumed to be cold-blooded in the reptilian sense, sluggish animals dependent on external heat sources to stay active. The picture has been steadily eroded by evidence over the past few decades, and a 2022 study added some of the most direct chemical evidence yet. Researchers led by Jasmina Wieman at Yale applied two complementary spectroscopy techniques, Raman spectroscopy and Fourier transform infrared spectroscopy, to fossilized dinosaur bone. Both methods work by measuring how a sample interacts with light, providing a detailed chemical fingerprint of what's actually present in fossilized tissue. The team was specifically looking for advanced lipoxidation end products, byproducts of metabolic activity that accumulate in bone tissue over an animal's life and survive the fossilization process largely intact. Faster metabolisms leave behind more of these molecular markers. Across roughly 30 dinosaur specimens analyzed, every theropod tested, T-Rex included, showed metabolic signatures consistent with modern warm-blooded animals, birds and mammals, rather than with cold-blooded reptiles. The implication is that T-Rex generated and regulated its own internal body heat, a genuinely warm-blooded predator rather than a sluggish, sun-dependent reptile. That finding connects directly to another long-running debate. Did T-Rex have feathers? Evidence from feathered relatives found earlier, including smaller tyrannosaurids preserved with clear protofeather impressions, had raised the possibility that T-Rex itself carried some form of feathery covering. But direct skin impressions recovered from T-Rex specimens, including a well-preserved specimen examined by researchers at the University of New England in 2017, show no evidence of feathers on the areas of skin preserved, primarily around the neck, hip, and tail. The warm-bloodedness research helps explain that apparent contradiction rather than deepening it. For a warm-blooded animal, body size and heat retention are directly linked. The larger you are, the more efficiently you retain internal heat, since a large body has proportionally less surface area relative to its total mass. A small, young T-Rex might genuinely have benefited from insulating feathers to stay warm, but once that same animal grew large enough, retained heat would become a liability rather than a benefit, and insulation the animal no longer needed would likely have been lost over the course of its multi-decade growth to adulthood. The current working picture is a T-Rex that may well have hatched with some form of downy covering and gradually lost it as it grew into the large-bodied, heat-retaining adult recovered in the fossil record. An extraordinary sense of smell, vision, and hearing tend to dominate popular discussion of predator senses, but recent research suggests T. Rex's most sophisticated sensory tool may have been its nose. T-Rex skulls preserve unusually large olfactory bulbs, the brain structures responsible for processing smell, a detail paleontologists have long noted from skull endocasts. What's new is a more precise estimate of just how sophisticated that sense of smell actually was. Researchers combined the physical size of the olfactory bulb, measured from skull casts, with genomic data drawn from living birds and reptiles to estimate how many functional smell receptor genes an animal with a comparably sized olfactory system would likely possess. More receptor genes generally translate into a richer, more finely discriminated sense of smell, the capacity to distinguish between a wider range of distinct odors, rather than simply detecting that something smells present. The resulting estimate puts T, Rex's olfactory receptor gene count, at somewhere upward of 600, comparable to a domestic cat, and higher than any other theropod dinosaur studied to date using this method. Researchers involved in that work have suggested this level of olfactory sophistication would have allowed T. Rex to detect the scent of blood or carrion from considerable distances, tracking wounded or dead prey across a landscape the way modern wolves or vultures do. In practical terms, that means a T-Rex quite plausibly located prey by smell well before it ever came within visual range. Eyes built for the hunt. Smell wasn't the only sense working in T-Rex's favor. Skull anatomy indicates forward-facing eye sockets that would have provided a meaningful degree of binocular, stereoscopic vision, the kind of overlapping visual field that allows an animal to judge distance and depth accurately, a genuine advantage for a predator tracking and closing in on moving prey. Estimates of T-Rex's binocular field of view put it in a range comparable to modern hawks, animals renowned for visual acuity and precise distance judgment during a hunt. Both crocodilians and birds, T-Rex's closest surviving relatives on either side of the reptile-bird evolutionary split, retained color vision, which makes it reasonably likely T. Rex did as well. Combined with a wide stereoscopic field and an exceptional sense of smell, the picture that emerges is a predator with a genuinely sophisticated multisensory approach to hunting, closer to a large, deliberate apex predator methodically working a landscape than a nearly blind brute relying on raw size and aggression. How we got the original picture wrong. To appreciate how much has shifted recently, it helps to remember how shaky the foundation actually was to begin with. The first mounted T-Rex skeleton, assembled by the American Museum of Natural History in 1915 from bones collected by fossil hunter Barnum Brown over the preceding decade, was built from an incomplete set of remains, filled out with informed guesswork and, in at least one documented case, borrowed anatomy from a different species entirely. Early reconstructions gave T-Rex a three-fingered hand copied from the related but distinct Allosaurus, before more complete specimens confirmed T-Rex actually had only 2 functional digits per hand. That original mount also stood upright, tail dragging along the ground, in a kangaroo-like pose that became the standard image of the animal for the better part of 6 decades. It wasn't until the 1970s that researchers, examining how T-Rex's vertebrae fused together and where its ligaments would have attached, realized that posture was anatomically implausible. An upright spine with the head balanced directly above the hips would have put serious strain on the neck and spine in a way the fossil evidence didn't support. The far more likely posture was horizontal, body balanced roughly parallel to the ground, with the tail extended out behind as a counterweight, the pose familiar from modern reconstructions. That single correction also shortened the animal's reconstructed tail by several meters, since the original longer tail had been modeled on the assumption that it needed to function as a kind of third supporting leg. The broader point is that T-Rex has never really been a finished picture. Each generation of paleontologists has effectively worked with the same limited set of physical bones while asking increasingly sophisticated questions of them, and each new technique, whether it's examining bone microstructure, running CT scans, or applying biomechanical simulation, tends to reveal that the previous generation's best guess was incomplete in ways nobody could have detected with the tools available at the time. The current wave of research fits that same long-running pattern. It isn't really a single discovery so much as the latest stage in a 100-year process of slowly correcting course. Why so much changed in such a short window? It's worth asking directly why this particular cluster of discoveries, covering diet, appearance, growth, movement, and even taxonomy, all landed within roughly a 3-year span, rather than trickling out steadily over decades the way earlier revisions did. Part of the answer is technological convergence. Chemical spectroscopy techniques capable of detecting metabolic byproducts in fossilized bone, the kind used in the warm-bloodedness research, only became precise and affordable enough for routine paleontological use fairly recently. CT scanning of living animals, used to build more accurate soft tissue reconstructions, has become dramatically higher resolution and more widely accessible to research teams outside major imaging centers. Statistical modeling techniques used to estimate maximum possible body size from a small fossil sample size draw on methods borrowed from population ecology and epidemiology, fields that have seen their own significant methodological advances over the past decade. None of these tools were unavailable in principle 20 years ago, but the combination of lower cost, wider access, and refined technique has made this kind of multi-angle analysis practical in a way it simply wasn't before. The other part of the answer is more mundane but just as important: more fossils. Specimens like Scotty took over a decade of careful excavation and preparation before they were ready for full scientific study. The dueling dinosaur specimen sat largely unstudied for years before becoming available to the teams that eventually reclassified it. Every additional complete or near-complete skeleton adds meaningfully to a sample size that remains remarkably small relative to how many of these animals actually existed. A single new specimen, prepared and studied with modern tools, can sometimes overturn conclusions that had stood on a much thinner evidentiary base for decades. The ripple effects, still working their way through the field. Several of these findings don't just add new information, they retroactively undermine research that was built on top of the old assumptions. And paleontologists are still working through exactly how far those ripple effects extend. The Nanotyrannus reclassification is the clearest example. Growth curve studies, behavioral inferences about juvenile hunting strategy, and even some population estimates for T-Rex specifically relied, in part, on specimens that turn out to belong to an entirely different genus. Recalculating those studies without Jane, Petey, and the Cleveland skull isn't a minor footnote. It changes the underlying data set a meaningful chunk of prior Tyrannosaur research was built on. Some published conclusions will likely hold up once the Nanotyrannus specimens are removed and the analysis rerun with a cleaner sample. Others may not, and sorting out which is exactly the kind of unglamorous, methodical work that tends to occupy a research field for years after a foundational reclassification like this one lands. The size and mass revisions carry their own ripple effects, particularly for anything that depends on estimating how much food T. Rex needed to survive, how large a territory it likely required, or how population density across an ecosystem might have worked. A statistical model suggesting the true maximum body size set closer to 15 tons than 9 tons changes the assumptions feeding into all of those downstream calculations, even though no physical 15-ton skeleton has actually been recovered yet. Living with an incomplete picture. It's tempting, reading through a list of discoveries like this, to assume the T-Rex picture is now more or less finished, that scientists have finally nailed down what the animal actually looked like and how it actually behaved. The honest answer is closer to the opposite. Every one of the findings described here narrows some previous uncertainty while opening up new, more specific questions that didn't even make sense to ask under the old model. The lips finding, for instance, rests on indirect anatomical evidence rather than a preserved facial soft tissue impression. Cullen himself has been explicit that the debate won't be fully settled until a specimen with genuinely preserved facial tissue turns up, something that hasn't happened yet for any large theropod. The maximum size estimate is a statistical inference from population math, not a discovered fossil, and it will likely be revised again as more complete skeletons are recovered and the underlying sample size grows. The Nanotyrannus story, while now backed by 2 independent lines of evidence using different specimens and different techniques, still leaves open detailed questions about how the 2 genera actually divided up resources, territory, and prey within the same ecosystem. Questions that are only now becoming answerable because the taxonomic confusion has finally been cleared away. That incompleteness isn't really a weakness in the science. It's closer to the normal condition of working with an animal, represented by fewer than 100 reasonably complete skeletons scattered across a species that, by current estimates, included something on the order of 5 billion individual animals over its existence. Each new specimen, each new imaging technique, each new statistical method applied to the existing bones gets researchers a little further from guesswork and a little closer to an accurate picture without ever quite arriving at a final, settled version. Given how much has changed in just the past 3 years, there's no strong reason to expect that process to slow down anytime soon. None of these individual findings on their own is really the headline. The lips are a fairly narrow anatomical detail. The Nanotyrannus reclassification is, at its core, a question of taxonomy. The growth rate revision is a question of bone histology. But taken together, they describe a genuinely different animal than the one that's dominated popular imagination for the past 3 decades. This is a predator that grew slowly and dangerously over 3 or 4 decades, rather than reaching adult size within 20 years, accumulating hunting experience the entire time. It's an animal that likely moved with quick, controlled toe-first strides, rather than a heavy, stomping gait, capable of running down prey at speeds that would outpace an Olympic sprinter. It generated its own body heat like a modern bird or mammal, likely shedding downy insulation as it aged out of the size range, where retaining heat became a liability rather than a benefit. It hunted using an exceptional sense of smell capable of detecting prey or carrion from considerable range, backed by genuinely good stereoscopic color vision once a target came into view. And once its jaws closed, its teeth, protected behind scaly lips rather than left permanently exposed to the elements, delivered one of the most powerful bites ever measured in a land animal, kept in far better condition than the crocodile-style, weather-beaten teeth of popular depiction. And there's a strong chance it wasn't even hunting alone in its own ecosystem. With Nanotyrannus now recognized as a genuinely separate, smaller, faster tyrannosaur species sharing the same landscape in the same time period, the late Cretaceous predator guild that T. Rex operated within looks considerably more crowded and more competitive than paleontologists assumed even 5 years ago. We've recovered fewer than 100 reasonably complete T-Rex skeletons out of an estimated 5 billion individual animals that lived and died over the species' existence. Every one of the discoveries described here came from painstakingly extracting new information out of that remarkably small sample, using tools, chemical spectroscopy, CT-based soft tissue modeling, statistical population analysis that simply didn't exist when the first T-Rex skeleton went on public display in 1915. The animal keeps changing every time someone finds a new way to ask it a question, and there's no particular reason to think the process is anywhere close to finished.